statistics subject in general. Uh, we have been working for more than 2 years and under the Nilgiri Club. Hope I'm audible. Okay. Yeah. So this session mainly is. I hope you have attended the time series session before, since there was a wide response, basically, for particularly the time series session, and generally it has a wide range of applications in our daily life. This session mainly will focus on analyzing our time series data. Okay, so what we'll try to do throughout the session is we'll primarily give you an introduction of all the time series components or the factors that are important to be revisited. First, we'll brush up through it. Few of them you could find the familiarity in the slides. You have actually, if you had already attended the before session, but even otherwise, we'll go through everything once. And after that, what we'll do is we'll take up a real life data set, a real time data in Python. We'll import it. We'll go the step by step how basically you, after importing the data, how you clean it, how you visualize it, and how do you uh, approach time series data for the further analysis part. Okay, that is our course of action for the day. All of you can actually, the collab file which we will work on will be shared. All of you can actually go hands in hands, we can do it together as well. If you have any queries at any point of time, please do ask away. Okay, and just to a very small briefing of the session, sorry, of the club. We basically work more towards the statistics subjects. As you have seen, we have conducted more than 10 sessions through different terms, and we had a session for hypothesis testing in time series predominantly. There was session for probability too. All of these you could find in the Nilgiri's YouTube link. As well, we conduct a weekly quiz competition. This will actually be continued this term also. All of you, please do try to participate. At least all of you would get the top lead players of it would get a certification as well through this quiz. Through this workshop session, while okay, you could just pay a little bit of attention to the theory part so that it doesn't bore you so much. There will be a quiz, a quick quiz session where we'll paste you the link where you could answer it. And yes, and all of you could actually get a certification for this workshop. Okay, any doubts? Any doubts, guys? Or do you have any suggestion? Okay, you could at least speak up. No issues. Okay, perfect. I hope I didn't miss anything out. Okay, so let us start with the session. Yeah, sure. We'll completely give you an introduction. I'll give you a very thorough basics of whatever you need for time series. You don't really have to have any kind of pre-notion about it. Even of the subject statistics, you might not need. You just will do a proper analysis. Yeah, sure. We'll provide the YouTube link of Nilgiri's. I'll paste it in the chat, okay, before the session ends. So we'll put the thorough terms that we'll come across, that mainly the subject of time series, as well whatever is required in this particular session. Okay, all of this will be discussed. There is no issue. Any one of you can actually participate well enough. No issues with whether you have actually been on a session before or not. That is not going to make an issue. Okay. And just for the view, I'll probably close the window. So if you message, maybe I'll not be able to see the messages. So just hold it.
Yeah, I'll be letting you know if there was
Okay.
a queries or not.
Yeah, thank you. Or any, if you want, you can just unmute and ask. Okay. This is a okay. The first introduction part that I'll be taking will just be a theory part. So, yeah, we'll give you the club WhatsApp link also before the session ends, and we'll give you the G Space link also. No issues. And Samibrata will be taking the total analysis part as of now. So you're free to ask any of us anything. Can we just start for the evening? Okay. Um, Sorry, that was his last link. I was just brushing up. Okay, so here starts. Okay, the event is named past, present, and predict. As you all of you would know, time series data basically when we use in an economic terms or in a business term. These are few of the important fields where time series is very widely used. Okay, it has got a very wide application, particularly in these two scenarios. But you can see a tons of other scenarios where time series is useful. So what do we usually use a time series for? If you could think of generally, the basic examples that we could relate is maybe in a business, the owner would like to know, or a manufacturer would always like to know, what is the sales that would come in the upcoming season, right? Or maybe in the next month, in the next week, so that he could have a stock up of the things that he needs. Maybe if it's a stationery shop, as soon as the school reopening starts, I guess everyone would be crowded around a stationery shop, right? To get notebooks, pens, and pencils, bags, every sort of things. So we, the owners, or even the manufacturers, always try to anticipate what would happen in the nearest future. Okay, this is where the time series data actually help to forecast what is about to come. Okay, if you do not want a very simple example like this, you can always take the weather prediction example, right? You always see a 1 week forecast in your mobile phone, and you would maybe rely upon it to decide whether you need to take an umbrella with you or not, a day, particular day, right? Maybe not so reliable in India, but otherwise generally people do that, right? So a time series data, one of the main applications of it is to study or to get a forecast of your nearest future or according to your needs. So as a time, the definition of time series is just a data wherein the data is collected through a period of time. Okay, it has been collected for a period of time in equal intervals. We usually consider equal intervals, but yeah, you can, but an unequal intervals is not so helpful for prediction, but it is purely a function of time. Okay, so what you have is okay, this is a definition, a formal definition written in your screen. It can be defined as a set of observations of a variable recorded at successive intervals or point of time. Okay, or mathematically yt is equal to f of t. Yt is where the value that we actually want to forecast upon, the variable that we actually want to forecast upon, that is called yt. Okay, they are the response variable. You can simply call it a response variable. You want to know a few set of variables are influencing your particular variable. Whatever is the outcome that you want to measure, that is denoted by yt. Basically, we have a measurement of these observations, or whatever factors we think is affecting this y. We'll have all those variables lined up, or we collect data on all those variables, and for at a point of time, and collect it for a uh, larger interval. Okay, now generally,
Ma'am, may I
yeah,
ask one doubt?
yeah,
So
sure.
let's say this stock price. Can we say the stock price is a time series data or it is in different category?
No, stock price is clearly a time series data.
Mm,
Huh.
okay.
You do a stock analysis using the time series condition only. If you really want to do a stock price analysis, you can directly, maybe after the session, you could try that. Go to a Kaggle page, get a stock price data, and you could directly analyze it. It is purely a time series data, because if you could just see, you could see the stock price maybe opening, what was the highest, what was the lowest, and maybe what is the closing price of a stock. I gave you two for a particular day, right? For each day, you could count these four measures at least. So you have four variables. What is the final stock price? That is going to be your y. The values that, okay, I roughly told four factors, not that not necessary that these are the only factors, but yeah, you could consider that what was the opening stock price, what was the closing stock price, what was the highest value of it, lowest value of it, into your data analysis, and collect this data for maybe 30 days or 90 days preferably, and you would get a nice analysis result. Okay, to see if it's on a moving, I mean, like if it's going up, if it's going down, you could actually very neatly analyze upon it. But always consider having a little more data, and 90 60 to 90 is a very fair number. And why do we use? Yeah,
Would like to interrupt, Shikana.
yeah, yeah.
If anyone is trying to work on stock price data, then they should visit either Yahoo Finance or maybe Nasdaq. So you will be getting the authentic data from over there. And apart from that, for any time series analysis, it is required to have at least 25 data points. So at least 25 data points you need. If you are working with monthly data, you need to have 25 months data. If you are working with yearly data, then you need 25 years as data. And if you are working with daily data, you could just work on 25 days. So if you are interested in working with stock price data and something like that, financial data, you should visit Yahoo Finance. That's the best source you can explore. Yeah, you continue.
Why 25?
To actually get the trend scenario, it is required to get at least 25 data points.
Okay, based on trial and error method, right? No rules.
Uh, no, actually, there are few equations that sets well if you are at least having 25 data points, and it is basically to get the trend scenario. Otherwise, you could analyze the seasonality and all, but trends are often explainable if you have at least 25 data points.
Okay.
Is it like in Stat 2 we were told that sample size should be minimum 30 to work with? Is it something related to that?
Okay, basically the 30 is a very theoretical value. Okay, upon which the theories are developed. 30 is not a very large sample. If you actually look into stats too, they'll simply say that 30 is a large sample. Above 30 is going to be your large sample case. Okay, but that is not so in reality, because we have a wide range of things happening over time, and 30 is theoretically a very ideal number. But the more data, the better your analysis would be. Okay.
Yeah, okay.
Cool. So generally, as we just discussed, what do we use time series for? We use it to see how the data is moving, how it has behaved before, how do we plan for the future, as well to compare how a particular same thing, maybe the weather condition itself, how it is moving in the southern part of India and the northern part of India. Okay, you can see the extreme changes or the very little changes, how it is happening at different places at different points of time. Okay, as well you could see what are the factors that is which factors are affecting in which format. Okay, just as Amnibrata now said, you have a trend factor as well as a seasonal factor. Each of them have a different impact on your data. So to study objectively each factors and how they are affecting your final output, that is where the time series mainly comes into play. Now, as we just said, there are main four components of a time series, which are trend, seasonality, cyclic, and the random component. Okay, so you have a time series data, which is just a sequence or a collection of a data, and main four components that are included in any time series data is going to be trend, seasonality, cyclic component, and the random component. As plainly as the word says, trend is nothing. You could just use it as the common colloquial term that you always use among things. Trend is whatever is happening or the long term movement of a data. Okay, how in general the data tends to move. Okay, in general, but that doesn't always mean that the trend thing all, I mean, like the trend component should always be on an increasing path. That is, it should increase by a same proportion or a different proportion. It doesn't mean that over a long period of time. Now long period is again a very relative term. You cannot put the long period for, equivalently for every scenarios, right? Maybe for a stock price 30 days is a long period of time, but whereas if you look into some bacteria reproduction, hours is even a long, relatively long period of time, right? So according to the scenario you need to consider, and whatever is the long term behavior of your particular data, that is what is known as trend. And as said, even within that long period, necessarily not that all points should keep on moving up. Okay, it doesn't mean that. It just means that on a, if you consider the whole interval as a complete structure, you could see that the movement is in general on an upward path or on a downward path, and it is possible that the data shows no trend at all also. It is not necessary that every data should have a trend component, but trend is one of the component that is usually seen in a time series data. Now next is the seasonal component. This is also pretty very visible and understandable from its name, I guess, right? The It is natural that the umbrella sales would go up in the rainy season, or you could say the stationery went up in the school reopening season, right? So whatever it, this is these, I the first example that I gave was due to a natural cause, right? It was just a weather condition that made it. The other one is a man-made cause. So both of these factors could affect the total sales of whatever whatever product that you're considering. But the movement of these sales are based on the seasonality. Now seasonality is just the one thing that these patterns recur within a year span of time. It cannot be more than 1 year time period. The seasonality, that whatever you observe in your data, usually you could very visibly observe it in a quarterly data or a monthly data. But then a seasonality, whatever we are considering, the pattern should repeat within a 1 year period. It could be any time less than the 1 year span, but when it is less than or equal to the 1 year span, we call it a seasonal component. And the other component where it is the long term affection and it does not have an maybe an equal pattern of repetition, that is called the cyclic component. Okay, cyclic component has a time period. The pattern repeats over a more than a 1 year span of time period. And you could see that, just like if you're familiar with the business cycles, they are the 4 cycles that are affecting a cyclic component: the prosperity, where it increases, the recession, the depression part, and then you have the recovery. Okay, these are the 4 components that are generally, or the cyclic components, like a division within the cycle, like I said. But yeah, you can, if somebody is from the mathematical background, you can see this is just a sinusoidal wave structure. Okay, the only thing is that the cyclic components takes more than 1 year span. Okay, and the last component is a random component, which we cannot account to in any of the other factors. Okay, other than the trend, seasonal, and the cyclic component, any other factors that is randomly influencing your time series, that is called the random component. Okay, so what are the 4 components? The 4 components ought to be time, trend, seasonality, cyclic, and random component. Okay, now the random component, as said, it cannot be generally measured. We cannot directly measure it. Not that it cannot be ever measured, but then yeah, we cannot directly measure it, and there are no much of like, in comparison to the other 3 components, you don't have wide range of applications, or sorry, tests to actually measure this, basically because of its unpredictable nature. Okay, because we cannot isolate it, as well as we it has very fluctuating nature. We never know when it is there, and also it is omnipresent. Many of the any of the data will have a omnipresent natural variance happening within it, so you really do not know when or how it would happen. Okay, that is why random component is generally not measured. For the same reason, our analysis mainly goes by the our forecasting, or whatever we do with the data, we concentrate on trend, seasonality, cyclic component, mainly to dissect our data. Okay, now before coming into more complicated terms, a quick recap. You have generally two types of model that you consider. One is the additive model. Additive model is when you believe that the 4 components that we just discussed now are independently acting. Okay, they one do not influence other. Of course, this is a very theoretical thing. In reality, is very tough to get such a model. So it is little rarely used in comparison to the multiplicative model. But you use this particular model in case you have these three components acting independently of one another. Okay, and as the name suggests, you add the trend component, seasonal component, and cyclic component with the random component to actually get your final response value. Okay, next is the multiplicative model. We use this when the terms are dependent on one another. Okay, this is where each component actually affects the one another. You are pretty sure that all these components are influencing one another. Now, it doesn't mean that you should directly use it like this. You could always mix it up. Okay, like take trend into seasonal component plus cyclic into random components. You could make any number of combinations with these four factors with a mixed model. Yes. Okay. To get a mixed model. Not these are the basic models that we use. That is the additive model and the multiplicative model. But we could always use a mixed model. That is a mixed combination of the additive model and the multiplicative model. Remember that you use an additive model when you have an independent factors affecting your response variable. And if you have the different components of the time series depending on one another or influencing one another, that's a better term, then you should preferably go for a multiplicative model, and not necessary that you use this particular multiplicative model. That is, everything should be in multiplication. There is no strict rule like that. You can use any combination of it. Very clearly, if you could say that whatever sales data that whatever example that we were considering from the first, it has got a very less chance that it will have a cyclic component, right? If it is the sales of your stationery, the predominant component is mainly going to be what? The seasonality, and then comes the trend component, right? Usually you have a very constant trend, but it is still increasing trend because maybe our parents wouldn't have probably used this much of stationery as much as we use, right? We like, even when we were in schools, I don't remember using a sticky note or a pointer or something like that. Even a highlighter was little rare maybe. But then as you came to the college, you started using those stationaries. So but if you see your parents age, they'll use one book for 10 subjects. We never did that. So I mean, not that we couldn't do, but yeah, the way the pattern of using those stationaries have changed gradually, which is on an increasing trend. So instead of getting one book, now we are getting 10 books for 10 different subjects, right? So there is a naturally an increasing trend, and this is a very plain random example. Okay, you could think of any scenarios that you could relate yourself to, and you could see that the seasonality is very evident after the reopening season. Maybe around the March or April, during the summer vacations, the very rarity that somebody would go to a stationery store and get you some random notebooks and sketch pens, right? It is little lesser on the side. The chances are little going to be low. So that is going to be the depression stage. It will just start recovering as soon as it hits May or something, probably, right? And basically, okay, these are the two models that you use in a time series. You use to picturize a time series. Okay, now this is a different term that if you had attended the session, you might not have heard of. What is stationarity, and why is it important to have a stationarity? As students of stats 1 and stats 2, you might have always heard the test that we are doing in hypothesis testing basically has a set of assumptions, right? Or even if you go into the regression part or any testing part, usually the statistical concept works with a set of assumptions, because if everything dynamically changes, it is not so easy to actually ring up something, right? So what we generally do is we have a set of assumptions while modeling and while testing your analyzing your data. One of the very important assumption of your time series analysis is stationarity. Now, stationarity is not that a very complicated term. It just means that your whole time series has a constant mean term, has a constant variance term, and a covariance term. You know what is mean, variance, and covariance. Mean is the central tendency of the data. Variance will give you it is one of the measure of dispersion of the data, and covariance is how much linearly related are the two factors affecting a data or factors in a data. Okay, so these values are independent of the time t. Okay, it does not depend upon at which point you are observing these factors. When you have a constant mean and constant variance and constant covariance in a particular data, you say that your data is under stationarity. And if it is not, you say that it is non-stationary. Okay, no doubts, you have a constant mean, constant variance, and constant covariance to your data set for each factors of your data set. And then you say that the time series is stationary. It is important because most of the theories are built upon it and it gives a stability to your data. Okay, because you need to know how each factors has gone through for a long period of time. Now if it is just dependent on that period of time, because maybe what did you say, you see that you saw that the sales dip, if you are considering the pandemic time period, it was probably affected just by the pandemic, right? Now if it is just a particular scenario, then you cannot base it upon for a long term period analysis. That is not a fair thing or even a logical thing to do, right? To give you more insightful and stable understanding of your data set, it is important that your data is stationary. Okay, now if it is not stationary, obviously 100% most of the data that you actually have in real time is not stationary. Okay, is not going to be stationary. You will encounter more than enough of your non-stationary data. So what you need to do before doing an analysis is convert the non-stationarity or eliminate the non-stationarity of the data so that you get a more stationary data. Okay, so non-stationarity data is what you observe. What it was, it did not have a constant mean and covariance in your data. So when you have that, you have different measures or basically linear transformations or non-linear transformations so as to convert it into a stationary data. I have just listed a few of the factors or methods of these converting it. One is applying the transformation. Maybe you, if somebody would have taken an analysis, actually, you could see that a quadratic expression, when taken log or something, you could actually convert it into a linear form, right? You could apply a log transformation, or you could do a square root transformation, cube root transformation. There are n number of transformations that are available with you. You could do the transformation so that your data starts acting stationary. Okay, these transformations do not affect basically the basic structure of your data. That is not happening because you are applying this transformation to every possible data values or every possible variables. But still, when you apply the transformation, few data set may behave as stationary. Okay, remember that it is a may, not always the log transformation is going to work, or not always the square root transformation is going to work. Okay, there are different set of transformations. You need, if it is not, if one is not working, you need to switch to the next technique. Okay, so it is not that there is a strict rule. For stock you need to do log transformation, for GDP data you need to do a differencing or something like that. No, there is no hard and fast rule like that. It depends upon the nature of your data. It varies depending upon the nature of your data. Another one is deseasonalization,
Shivana, I
detrending.
guess we got a question.
Yeah, sorry.
What is the need of transformation here?
Because that's what I said. The data is behaving non-stationarily, right? So that you could make the data as stationary. That is why we are transforming.
In general, the data would be non-stationary only. No?
Yeah, in general, most of the data that you are encountering is going to be non-stationary. Very rarely would you get a stationary data.
What is the use of converting it?
Only then could you do proper analysis. It is a need, not a merit. It is really a need. You can, the non-stationary data is actually a very it is influenced a lot by the time. Okay, so when it happens like that, it is very tough to get a stable outcome out of it, outcome out of your analysis, to understand each factor separately. You cannot do that in a non-stationary data, because every time you encounter something, the time period at the time point you collected the data would influence your analysis. Is that okay?
What are the bullet points
What are
mentioned here to transform non-stationary to stationary? Those are the methods you are
Yeah,
talking
these
about.
are the methods.
Okay, so using log and square root, those are not linear, right?
No, need not be linear.
But it will convert non-stationary to stationary,
Yeah,
right?
yeah, right, exactly.
Okay.
This is fine. Another thing is differencing. Differencing is just where you have two consecutive observations and you will subtract the near adjacent observations with each other. That is a form of differencing that you would do. Or you could just separate out the trend from it. You know what is a trend component, or you could just, there are methods to actually just find out what is the trend values in the data. You could just remove them. Maybe then the data would be stationary. We don't know. It depends upon the data. Okay, so you need to find which factor is affecting the stationarity of the data. Maybe do some transformations, some sort of transformation, any of these transformations or any other available transformations, and then see if your data could be converted from non-stationary to stationary. That is a primary step. Now, how do you check if your data is stationary? You need to do the check, right? Unless that you don't know if it is stationary or non-stationary. That part, generally, this is one of the tests. Okay, not necessary that this is the only test. This is one of the tests that is used I have stressed upon it just because this is the test that we will be applying into our data set. But then this is one of the tests that you could use. What we test here is we have a null hypothesis that the data is not stationary. Okay, and automatically the alternative hypothesis is going to be the data is stationary, and we would just test use this test directly. And if you have this is the basic testing procedure. You don't have a very complicated thing or even anything to recall so much. It is just from your hypothesis testing part. If you have a small p-value, what was this p-value? It is how much evidence that you have against your null hypothesis. So if you have a small p-value, you would reject your null hypothesis. Okay, so you can reject and conclude that your data is already stationary. Now if you have a high p-value, you would do the reverse thing. Okay, you could actually, there is a covariance function where you could actually plot the covariance value of each of your adjacent time series data, or even not even necessarily adjacent, maybe what with a difference of h or something. You could, like, what h data is apart, that is what I mean. Like if you're plotting a1 and a6, this is 5 data apart, right? Like that, you could plot the covariance factor between a1 and a6, where a1 and a6 are two data points at 1 and the 6th point, and then you could see how the covariance function moves. Okay, so if it's a stationary covariance function, it would diminish out fast. If it is not, it will not. So there is a pattern even in the covariance function. There are other tests also, but what you do is, this is one of the tests that we have used, which has a null hypothesis which states that our data is not stationary. Okay, you could use a direct formula for this. Now let us see what are the standard time series models that we have. Okay, now what are models? Models are something that okay, you saw an additive model and a multiplicative model, right? Similar to that, you have the factors which is affecting, depending upon the factors which is affecting your data. If you could say what type of a time series it is more easier to analysis. Why are we doing this? Because there are different factors, components which could actually give you insights. Maybe if you, when you study the probability distributions in stats 2, if you have not studied, it's okay. Okay, so why did we actually use the binomial distribution or monomial distribution? Because we already had some sort of characteristics sorted out for those named distributions, right? These are few factors, or these distributions are few things that we repeatedly saw in our nature. And what we wanted to do was, if you could fit your data in one of your distribution, so that you could get more meaningful insights from it, right? And you could readily gain the data also, I mean readily gain the result also. You do not have to wait for ages to actually get something out of it, right? Okay. That is why we actually use the standard models or standard distribution. Similarly, standard time series models we use so that we could fit our data into one of these models, or understand the behavior of our data through one of these models to gain better insights out of it. Now let us see what are each one of them. First one is an AR model. Okay, AR model, or it is actually called auto regressive model. Okay, there's a small mistake. Okay, actually auto regressive model is the lower portion, and MA is this one. I pasted the image wrong. I'll correct that when before giving it to you, but just for now adjust, I'm sorry. Okay, auto regressive model is where your response variable is depending upon the same response variable but with the of the past period. For example, you say that your, maybe it is your expenditure. Okay, this month's expenditure, what you do, what you maybe expend on a luxurious food or a date out, a restaurant outside, is going to be compared to how much you spend the last month or the previous month. Okay, so when your data, when your response variable actually depends upon a lag is what? Lag is how it behaved on a previous time period. Okay, it could go lag up to any periods. Here what is given is lag up to p periods, right? Yt is your current variable, and it is depending upon yt minus 1, yt minus 2, etc., yt minus p. So up to t periods, up to p lags, the current variable is dependent. Okay, so when a variable is dependent upon its own previous lags, it is called to be an auto regressive model. Okay, the second is where your current value is depending upon q lag. This is just a random term, it could again be p lag, but p lag not of your dependent variable but of your random component. Okay, if you generally see et is a random, epsilon t is actually the random component, or you call it the error term. Okay, or the white noise, that is what the standard term used for it. But then when your current dependent variable is actually depending upon the previous q, according to this equation, the previous q error disturbance term or the random component of q lag, then it is called a moving average time series model. MA is moving average. Okay, AR is auto regressive, MA is moving average. Now you could just get what is ARMA, right? ARMA is just a combination of AR and an MA model. You have, if you see this equation, you have YT. This is your response variable. It is depending upon P.
Ma'am,
Yeah, please.
hello. Can you please explain moving average?
Sure. Moving average is where your current response variable is actually dependent upon the previous q lags of your random component rather than your own response variable. It is dependent upon previous q time periods random component. Okay, there were four components, right? The trend, seasonality, cyclic, and the random component, or the error, whatever it is not accounted for in these three components. That is called the error term, or the disturbance term, or the random component. All these are the same terms. You just use in different scenarios, different terminologies. Now, if those affect us, those factors, not just of this particular random component, it is not just affected by this particular time period, but you have a disturbance term affected as some minor things of your previous q time periods, then that is maybe what you can say, your expenditure. For the same example, maybe this is not a very ideal example, but then still let us go with it. If your the expenditure of your current month, yes, it is dependent on your current income, fine enough, fair enough. But maybe it is also dependent upon, if you have so much of unexpected expenditures, it is already depending upon each times how much savings you made. Okay, how much you are not supposed to expend your savings, right? So maybe it is account to a very small portion, I'm assuming so. If like that, and it depends upon how much, if it depends upon how much you saved in the last 3 months. Okay, if it is like that, if I'm considering the error component or your savings to be a very minute amount, okay, if it is not actually affecting you, it is unaccounted for. If you are considering it like that, how much ever your error component is affecting your current response variable, that then we actually model the data to be a moving average data. Is it better? Okay now?
Okay. Yeah.
Okay, thank you. And then you have a combination of these both, where your response variable is dependent upon P previous, your response lags, as well as Q previous error terms. Okay, you have both of it in your model. You have the error term, I mean lagged error term, as well as the lagged response variable affecting your current variable. Okay, then it is
Ma'am,
where, yeah,
is Q an integer like Q previous
yeah.
lags you are talking about?
Yes, yes. P,
Okay.
Q are all just integers. Some time periods, 3 months, 5 months, 1 year, 2 year, anything it could be. It
Okay.
is just whatever measurement, the time T that you are considering. If it's a month, then it Q would be some 12 months, 8 months, anything it could be, any number it could be. It's just number.
Okay.
And that is why, yes, that is why it is coming up to the right hand side, because it already happened, you have observed them, it is known to you. Unlike the YT, the current term which you are measuring or which you are trying to predict, unlike that, these factors, T minus 1 factors or T minus P, T minus Q, all these factors are something already that had happened in the previous time periods, and it is known to you. Okay, that is why they are already predetermined. That is why these are coming onto the right hand side, so that you could use it. How much you can see, how much it is affecting, or maybe you can just think of, maybe the our finance minister made out a statement. Okay, made out a new policy on income tax return. It is not going to affect you in that particular accounting year, right? It, you would only exercise that in your next accounting year. Your savings or investments will not depend upon the, she usually announces it in February. It is not going to be affecting that particular accounting year, right? So your next year's investment plan is actually going to it is actually going to depend upon the previous year's budget or the announcements. So there is a lag in the affecting, right? That is what we are accounting here for. Now the next is ARIMA model. ARIMA model is the same thing. It is an combination of autoregressive and moving average model. But what could happen is, if you apply the differencing method, I hope you remember what we just discussed, the differencing method that we use to convert a a non-stationary time series data into a time series data. So if you apply a differencing into your data set, if you could, into this combination, okay, into this combination of ARMA data set, if you could make the non-stationary data into a stationary data upon maybe de-differencing, that is again a number, okay, upon 2 differencing or say 4 differencing, you do the differencing these many number of times, and if you could make your data stationary, then you could directly fit an ARIMA model. And ARIMA model is one of the most famous and the most common, widely used model. Okay, and then next comes the Sarima model. It is again just the seasonal component added to it. Okay, a model that could handle the seasonality component of your data. Fair enough? Any doubt before I actually finish it off? The theory part is done. You don't have to think a lot about it. Just remember the important terms. What were it? The time series, it is a collection of data where you have it over a set of time periods of time, and the primary factors that actually affects the time series data are the time component, seasonality component, and the cyclic component together with the random component. The random component is omnipresent, which doesn't have a pattern. It is unpredictable in nature. The cyclic component, it is a pattern that is observed in a data where the pattern is happening for a more than 1 year time span. It doesn't happen within a year. It takes longer period of time to execute. The third is a seasonality where you have which could actually happen naturally or it is man-made. It is a repetitive pattern that you can observe in your data within a time span of 1 year. And the final one is the trend component, which is the long-term pattern of your data. Okay. Is the theory part clear? Do you want to ask any questions? Okay, but what we are going to do now is just take a data and then we'll see how to import it into our collab file. We'll do an elaborate visualization upon it, which is actually called the EDA part. And we'll try to fit a proper one of these models that we just discussed. We'll try to fit one of these models, see if there is stationarity in our data. If there is stationarity, then if there is non-station, if the data is behaving non-stationarily, we'll try to transform it into a stationary data, and then we'll try to fit into one of these models and see if we could forecast a value. Any doubt? Do you want to ask anything?
Ma'am, can you briefly explain about ARIMA model again?
Okay. ARIMA model is, it is you have a combination of autoregressive and moving average model. Okay, you have a data like that. Now, that data is behaving non-stationarily. Basically, if you see what is the nature of the data, it is behaving non-stationarily. Okay. Now, if you do some differencing into it, maybe you're differencing. What was differencing? Differencing was you subtract the adjacent observations, right? That is the process of differencing. Now, if you could actually difference the adjacent observations, and just because of that differencing, after the application of the particular transformation, if your data is behaving stationarily, then such data could actually be fit into an ARIMA model. And the differencing need not be of one time. You could difference the data repeatedly. Maybe you could difference it d times, or that is a usual notation for it, but you could difference it say 7 times. Okay, maybe, or if it just happened in one differencing also, not necessary that you need to go up to that, but yeah, if you are differencing, you could just difference your data, and then the data starts behaving as a stationary data, then such data could actually be fit into an ARIMA model.
So it is, can we assume that ARMA model is gives, it is also a combination of AR and MA, while
Yeah.
it is of stationary form from the
Yeah,
starting.
after differencing, it would be stationary. All ARMA is not necessarily act stationary after differencing, right? Only those after differencing which could make into a stationary category can be put into ARIMA, or best suited for ARIMA.
Okay, ma'am.
Okay, thank you. Yeah. Anything else? And yeah, the quiz is open now. I guess Sami brother would actually have. I have stopped sharing. Okay. Yeah. Have actually put into the chat or something. Yeah. Maybe.
Yep, I'm just putting it over there.
Okay. Thank you. Yes, Suraj, you wanted to ask something? Okay, just saw your hands raised up. Fine. Upon quickly, I hope you remember all the things that we just discussed. There is a quick quiz session. This is just a G form which will be pasted. Which is already pasted in the G chat. You could just quickly attend it, and by that time, Sami Brata will start the collab session.
Yeah, so we are done with the first part of our session. Now we will be working on a real world data, or maybe synthetic data. So the form is open, guys. Please make sure you are attending, and then we're gonna start. There are
We
10
need a,
questions. Maybe we'll start at 10. You guys.
yeah, you can actually give it till 8 o'clock. It's 7:52, right? So maybe
Yeah.
they can do a quick attempt on it.
Yep.
If you guys are willing, okay. If you guys don't want to, just say no. We'll not waste our time. Yeah, you can all give a quick attempt to it.
I guess my screen is visible to you. Someone asked about edema and ARMA. There's some difference, right? So there's one I extra in edema. So that stands for integrated, which stands for the number of D, which is how many times you have like done the differencing. Guys, we'll be starting the hands-on session at 8. So make sure you are not leaving.
If you guys do finish before 8 o'clock, you can tell us.
Sir, I have not received the link.
It is in the chat, right? I'll repaste it.
Okay.
Yeah. Is it visible now?
Yes.
Okay. In between, we had actually conducted a revision session for SAT 1 and SAT 2 last time as well, and it will be continued this term. Probably for STATs 2 for sure. STATs 1, maybe we are thinking of mock sessions, but oh, great. You guys are very quick.
Yeah, actually, I can see response are like having a spike.
Uh, they just heard, right? So it just they're very quick, I guess.
Mhm.
Very fresh in memory and was explained well.
Oh, thank you. We hope after this session you would all get a hands on real-time data or even some sort of time series data and do it by yourself. And at any times, if you hiccup in somewhere, then do reach us out. This session is a hands-on session of time series data analysis. Yes, Kalyani?
Yeah, I had a question about stationary data.
Yeah.
When you say stationary has the constant variance or covariance or
Hmm.
constant mean,
Hmm.
does it mean like in the quiz also there was this question regarding the stationary data that it
Okay.
means the constant increasing trend. So does it mean the constant variance means the same variance, or does it mean that it has the constant intervals and increasing and decreasing trend?
No, it is not at all increasing or decreasing. It is not dependent on the time. If it is increasing, it means that throughout the time, as the time goes on, it keeps on increasing, right? That doesn't work out like that. You have a constant value of it.
Okay, so it should be the same constant value as in the same value. Like
Yeah, exactly.
if it's 0.10 or if it's 0.25, then it should be 0.25 for the covariance should be 0.25 for all the data,
Yep.
like for all the
Like
times.
for that particular factor, not
Yeah.
necessary that it is for same. Yeah,
Okay. Okay. Got it. Thank you.
yeah. Perfect.
Yeah, Suraj, go on.
Ma'am, can you explain about additive model and multiplicative model again after the exam, after the test series, please? I seem to mess that up.
Oh, that's okay. I can just say it now. Additive model, you saw the four components of your time series, right? They are basically, yeah, you will get the data, Keshav. Sorry. So there are basically four components that are affecting a time series. Generally, they are categorized into those four things: uh, trend, seasonal,
Seasonal
cyclic,
cycle.
and the random. Right? So these four components, if they acting independent of each other. Okay, that means one is not influencing the other. To get the model, what you would do is you would just simply end up adding those models. Okay, adding those models in the sense, we'll just add t plus s plus c plus r to, sorry, I, to actually get in the model. Okay, just a minute. Yeah, this is how an additive model is. White is equal to t plus s plus c plus I, where the factors are, components are independent of one another. We use this preferably when they are independent of one another. Okay, and the
Yes.
multiplicative model is when they are dependent on one another. Okay, here what happens is, instead of adding up, you are saying that it is just a product of it. And in general, we don't directly use both these methods. Instead, we use a mixed model where you could make some combinations of addition and multiplication. That is, you could say t plus s into c into I. Maybe. Okay, it depends upon your data. Or you could say ts plus ci. I mean, t into s plus c into I. Any other combinations is possible. So what we generally do is we use a combination of it. But purely on a definition basis, you use additive model when the factors are, components are independent, and you use a multiplicative model when they are completely dependent.
Thank you, ma'am.
Yeah, perfect. You're welcome. Yeah, the revision sessions of Stat 1 and Stat 2 are recorded. It is available in Nilgiri's channel. I'll just paste the channel link, okay?
Yep. So let us start.
Yeah, the time is
Yes.
up, probably.
No, there's
1
partial
minute?
minute left.
Okay.
Meanwhile, I should be sharing the link of the dataset. So today we'll be working with airplane passenger data. It's a time series data collected over 1949 to 1960, I guess. So this is a monthly based data. So let me just share it for you. Please let me know if you guys are able to access it. And I would also recommend you guys also do this code on your own simultaneously while I'm doing it over here. So just confirm me if you are able to like access the dataset or not. Okay, fine. So good. So first, what we'll be doing, we'll be needing few package libraries. We need to install few bits.
Yeah, yeah. Just a second.
Yeah.
Yeah. Oh.
All set? Should I start? Shugarna?
Oh, I'm sorry. Just, sorry, sorry. Yeah, you can continue.
Okay. So we should be using few like installing few pips. Like I gonna be using the data stored in my Google Drive, or maybe I can use it from anyone's Google Drive with public access. So for that, I'll be installing this. Uh, yep. Yeah, Vicky, go ahead.
Since I am in a very remote area,
Okay.
I don't have like power connectivity. I am in near to the border. So can you share this code or like how I can get
After the
this
event, you
code?
all will be getting the code and the slides, everything.
So you will be sharing over the WhatsApp or to
The
the student
Google
mail ID?
Space only. In the Google Space.
Google Space only.
Yeah. And
And
also,
please share the link also so that whenever I get the power connectivity, I can access it.
yeah, sure, sure.
Okay, thank you.
So let us connect and install it first. These are prereqs, by the way. And now you guys have the file ID, right? So let me just access the file and make a URL like this. So I'll just be pasting the file ID and getting a URL like this, and then if it's loaded, then I can download the dataset. For that, I need to import few libraries, which is first of all is gdown, which is Google Download library. And once I'm done, the data is with me. Now, yeah, let me print the head of the data. Okay, so I have to import pandas. So I guess this is the data you all are able to see, right? Okay, so first, while we are having any data for analysis purpose, what should we do? Anyone? Like, what should be our first perspective to approach towards the data? To know about the data.
Clean the data.
Uh, like, of course, to know about the data, explore the characteristics, how it spread and all, right? So for that, we're gonna do a EDA. So exploratory data analysis to check if there's any outliers, missing values, and how it looks actually. So for that, what we'll be doing, first I'll check for missing values. So wait a minute. Yeah. I guess this will return me no, is null. This will return me the number of missing values we have in both the columns. So in months, we got no missing values, and passengers as well. So we don't need to do any data cleaning or interpolation or something like that. If we had any kind of such missing values, we must have done some interpolation, maybe something including uh, approximation, estimation. There are different methods like MLE, MOM, and different methods to uh, interpolate or something like that. Now we're gonna check for duplicates. For suppose for a particular month, 04/1996, they have collected the data twice. So if there's any such inconsistencies in the data set, we're gonna check for duplicates. So we don't have any duplicates over here. So we have a very perfect and clean data. Now we're gonna plot it and visualize it, how it looks like with a line diagram only. So let's just plot it. So for plotting purpose, we're gonna use just df.plot, and for plotting we need another package, which is, can anyone guess? Matplotlib, yes. So yeah. Now once we are plotting it, yeah, now you can see there's a upward trends we can assume from the data set, right? Or anything anyone can like interpret from the from the visualization. Seasonality, yeah, seasonality is there. Can anyone tell me if there's any station, if the data set is stationary or non-stationary by just looking at it?
Stationary.
Yeah, but why?
It shows the constant increasing trend, increasing and decreasing. Like it's
That's the trend, but why it is stationary or non-stationary, whatever.
okay, just by looking at it, it shows that increasing trend. So it looks like stationary. Otherwise, to decide, we'll need some more data to decide
Okay.
details.
So we'll check later. Now,
Like it has a constant variance for each, like for each
is
that.
it is it having a constant variance? Yeah, go ahead.
Yeah.
Uh,
So like there are various like mountain like structures here,
hmm. But are
moving
those
upwards.
peaks
So
are
for each,
homogeneous?
hmm,
Are those peaks are homogeneous?
uh,
Are are the
maybe
peaks
not.
looking alike? I don't think so. Yeah, Arijit, go ahead.
It's clearly a non-stationary data as both the mean and the variance is changing over time.
Exactly. By just looking at the variance only, like the spikes, we can predict that, right? Uh,
So for stationary, it should be a constant kind of thing.
yeah, constant variance and constant mean. So the
So
peaks, uh, there's a upward trend that I can visualize easily, but there's a peak, right? The length of the peak over here is very less than the spike over here, right?
okay, so for the data to be stationary, just by looking at it, it should be a straight line
No,
instead
no,
of
no,
this.
not straight line.
Okay.
Suppose there's a peak over here, same peak is being observed over here as well, or maybe a same peak over as here as well. So the
Okay.
spike, the seasonal spike should be homogeneous, should look alike.
Okay. Okay.
Cool.
Okay.
So
Thank you.
from just looking
So
at the
it should
table,
increase by the same number. Are you saying that? Like,
uh, kind of, but not necessarily same number, same scale. You can say
okay.
same rate of
Or
spike.
increasing, like increasing data can be considered stationary data.
Sorry, go again.
The increasing trend can be considered as stationary, or like is it related to stationary or non-stationary?
Trend is not really related to being stationary or not stationary.
Okay.
Cool. Now, uh, now once we are done with this, the months which we were talking about so far is not relevant to us anymore, right? So I'll just extract the time series data set from the whole thing. So the number of passengers from the DF has been extracted and stored in time series. Now we got an index, no months related to it. Okay. Now, as we are continuing our EDA, we should look for outliers. Though we can predict outliers from this diagram as well. Can anyone tell me if there's any presence of outliers? Yeah, Arijit, go ahead.
No.
Arijit, are you
Yeah. I'm here. I guess no outliers.
no outliers? Okay, fair enough. Yeah, Kalani is right. No, there's no outliers. But how can we check any visualization technique apart from line graph or something scatter plot we can use, or like something very specific to check for outliers only? Any diagrams?
If there is,
Scatter plot.
Scatter plot is one, of course. Apart from that, anything's like scatter plot just doesn't let me know about outliers only. It also shows the linear or non-linear uh, com- uh, dependencies, I would say. Yes, box plot, someone said. So let us draw the box plot of the data. For box plot, we'll be using SNS, which is Seaborn library only. So we need to import another library, that is Seaborn. Once we are done, let us draw it, plot it. So this is our box plot. Can anyone interpret how this box plot is showing us no presence of outliers? Yeah, go ahead. Arijit. Are you there?
Actually,
The mean is,
there is
sorry.
no point beyond those whiskers. So I guess there is no outlier, I guess.
Okay. Kalyani, you were about to say something.
Yeah, I was gonna say that the mean, sorry, the median is in the middle, like the mean line is in the middle, so it's like it's the constant kind of, so it shows the constant trend, so there is no outlier.
Uh, Presence of outliers in a data set is not really connected to any kind of data
Mean,
set. If
okay.
it is time series data, if any trend is available, present or not. So I would say Arijit was more correct. And yeah, exactly. So every data points are belonging between Q1 and Q3. So nothing beyond that. That's why there's no presence of outlier, I must say. Though there are other options as well to check for outliers, like IQR method, Z score. You can try that as well. Wait, let me check for messages. No data point outside the range. Yeah, that's true. Okay. So far, what we know about the data, there's no presence of outliers. It's a time series data, and it might show that it might show something about stationarity. Okay. Now we should also check for seasonality, isn't it? But we'll check. First, I'll go towards something which is more statistically correct and significant for checking uh, if data is stationary or not. So I'll go forward with ADF test. I guess you all are aware of ADF test. Shukarna was explaining how ADF test works, right? Any doubt? Anyone has any doubt regarding ADF test so far? You can ask. Can anyone tell me what gonna be our? Yeah, go ahead, Vicky.
So right now I'm studying the stats 2 only.
Mhm.
So I'm not getting the points like ADF tests and all whatever you're
Okay.
talking about. So
You ever been
I need to
introduced with hypothesis testings?
I need to first complete this thing and then I can understand better how it is.
No, like you ever been introduced to hypothesis testing and all?
No, 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 no.
Okay, so basically, we are trying to construct a test, hypothesis test, uh, to justify if there's any presence of stationarity and all. Okay. So, if you have the concept of hypothesis testing, that would be beneficial. So, in this scenario, ADF in our ADF test, our null hypothesis is that our time series data has a unit root. That means it's not stationary. Okay. And our alternative is obviously the time series is a stationary data set. Okay. For that, we're gonna just construct a ADF test. Okay. So for that, I gonna use ADF Euler function, which belongs to stats model package. Okay. this package called stats model, which includes almost every hypothesis testing we do, and we will be importing that, and we'll perform the ADF test on TS, the time series component which we had. Now we have a test statistic and we got a p-value which shows something like this. So can you interpret the significance of this p-value, like what it is denoting actually? This is a very high p-value, I must say. So what it is denoting?
I think we should accept the null hypothesis in this case, if I'm not wrong. Or
If, okay, so we should accept it or reject it.
We should accept the null hypothesis.
Accept the null hypothesis, yes. So what was the null hypothesis? Non-stationary, right?
Yes.
So exactly. So we have to make it stationary. So what was the universal or first and foremost method you can think of while taking transformation or something like that?
Logarithmic or square.
Logarithmic or uh, root or maybe square.
Square.
I'll go forward with log transformation first. Okay, let us check. I just transform it to a log time series, and then I'll drop the null values. Okay, because it could introduce new null values to the data set, and then I'll try to test it again to check if the purpose was served or not. So let's see.
No.
Now we got a p-value, again new p-value, which testifies the same scenario, right? So as Shukarna explained, in often real life scenarios, it might be the case where the log transformation fails. And here we go. So anything else? I'd not be going with transformations now. Now what should I do? I should go for differencing, right? Okay. So now I have taken the TS, the whole original time series value, and differentiated it for the first time and drop the null values. And again, now here I'll be checking if it is able to fetch the required p-value. Now, how can you interpret this? Anyone willing to interpret this p-value?
The p-value is quite low, as well as the static is highly negative. So we have a stronger evidence against the null hypothesis.
Yes, reject. But it's a borderline stationary, right?
Hmm.
So we should try. We have two options. We can differentiate it again, or we just differentiate the log transformed data set, which already had a lower p-value than the original. So if we go forward with differencing it again, it will increase the complexity of the model. So it's better if we go forward with log transformed values. Cool. So let us do that. And now we got something bigger. Oh, okay. Maybe then we should differentiate for the second time. Okay, let me do that. Yes. Now, this time we can actually accept our null hypothesis, right? Can we? By looking at the p-value, can we?
Yes.
Yes, we can. So, okay, once we are done, then now I will try to decompose my whole time series data into different components which we already studied so far, right? So for decomposition, I need a package. I need a package called uh, seasonal decompose from stats model only. Okay, I just gonna import that and I'll be decomposing the whole time series data set, and it will give me a decomposed result which should be plotted. Now, if I plot this, what can I see? So, someone was telling me, right? So, if a data set is having upwards trend, then should it not be stationary always, or should it be non-stationary? So, see, in this data, this is actually the trend component. Okay. Now, in AR model, what we saw in AR model, the data set or the new YT was dependent on the error of the previous term, right? So these are my residuals or the errors which gonna influence in that scenario. Okay. So far, we just did the exploratory data analysis for the data set. Clear? Any doubts so far? Like, do you think like we could have done or tried something else?
Hello.
Yeah, go ahead.
For p-value,
Yeah.
first you have changed from non-stationary to stationary uh, using difference, two times difference, right? Differencing.
First, I tried log transformation. It didn't work. Then I
Hmm.
tried with differencing two times.
So,
So our D,
yes. So after two times differencing, you are getting a p-value which is very low. So it is a significant value. So it is doing after two times differencing, not for the actual data set. Is it
no,
correct?
yes, actually.
So what is the meaning for that?
So to get rid of the stationarity, we need to take the difference, and based on that, we need to predict the differences only. Then once we have the new differences for the future, we can get back to our original data set, right?
Okay.
So we can not directly predict our future values, but we can predict the future differences which gonna be coming. uh, I guess I was making sense, right?
Hmm. Right, right.
Okay. So far, can you see any space where you could have explored a little about the data set? Do you have enough data set, enough information from the data for the data set? What do you think? We know the trend component, we know there's no outliers, we know there's the seasonal component presence, we know it is not stationary initially, then we transformed it. Now we don't need to know anything else to make an analysis, right? So far what I was doing is called exploratory data analysis. Now I gonna go for the prediction part. The data become stationary by difference in twice. Yes. So the difference which I am talking about right now, stored in TS diff2, is actually stationary. Clear? Okay. Now, we have observed that there's a presence of seasonality. So, should we work with edema over here? You guys, you guys have actually gone through all the models: air emard, edema, sadima. So, should we use edema over here?
We have to work with this Sarima.
Yes, because we have a seasonal component present, right? If it was a yearly data, we should have worked with edema because there's no presence of seasonality, right? Here we should go for Sadima. And in by stats model only, we have a package for dealing with Sadima particularly. This one, Sadima X. Okay. Now, I just can call a function to fit it into Sadima model. Before that, I have seen over here that there's a presence of seasonal components, right? But if there's any other method to check for seasonality without decomposing the dataset, is there any? Let us explore. So there's something called autocorrelation function, ACF, autocorrelation function for a dataset. So if we just plot the autocorrelation function with a certain lag, then then only we can just observe if there's any. Maybe we should be taking the lag at least more than 25. Why so? Because to get any scenario, any seasonal scenario, you need to observe at least 2 years data set, right? If you are working with monthly data, because at least after a year it will be repeating in seasonality, right?
Oh,
So for to get the scenario of 2 years data set in monthly scenario, we need at least 24 data points. And if we are asking for more than 2 years, at least we need 25 data points. So here I'll be taking the lag for 50 and I'll be plotting it. Oh, okay. So ACF is defined in plot is there, I guess. PLT got slow. Oh, okay. Yeah. I need a package for that. From stats model only. Yeah. Here I can see there's a seasonal component. Cool. Next. Seasonality confirmed. Stationary it was, and now it is not stationary, non-stationary, and we have done the EDA so far. Now I gonna fit it into Sadima, but for the sake of simplicity, I'll be taking a log transformation of the data set before fitting it, because it's what does log transformation do? Someone was asking in the theory part that why we are taking log transformation, it is not linear. Yeah, it is not linear, but log transformation always stabilize the variance, so it will help in that part as well. Now I'll be differencing sorry I'll be transforming it to log, and then I'll fit it into Sarima models. Okay? And let's see what the results come. Now, here I have mentioned that order 111 and seasonal order 11112. What does that mean? So basically, this is how our Serima function looks like. Wait a minute. Yeah. So, okay. Is there a question in chat? Let me check. Can you repeat the seasonality trick? Okay. Yeah, sure. So what I did, I just plotted the autocorrelation function with plot underscore ACF. I plotted the autocorrelation function and clearly I can see a repetition of pattern which indicates a presence of seasonality. And here I have taken lag as 50, so it will be plotting only 50 data points. Cool? Okay. So now in Sedima model, I have used order 1, 1, 1, which is P, D, and Q, right? So I have given the P, which is the value of AR, and Q as 1, which is the value of moving average, and differencing as 1. Why? Because I'm working on log transform data. And for the seasonality check, seasonal order, I have also given AR as 1, differencing as 1, and MA as 1. And period, I have given as 12 because I'll be checking the seasonality based on a year. So I'm expecting a pattern will be repeating each year in the data set. And we have the result. Cool. Now, as it was explained earlier, that AR works with the previous value, right? The previous value or previous month's outcome to predict the next month's um, value, right? So it's assuming that our next month's observation will be dependent on this month's observation. But this model will is having a coefficient of 0.169 and p-value 0.425, which is greater than our threshold, general threshold. So it is not statistically significant. So basically, in uh, the contribution of AR model in Sedima is not statistically significant. So you guys are aware of that Sedima is also a component of Sedima is a component of different models, right? AR, MR, MA, ARIMA, and all everything. So let's jump towards moving average. While we are taking a lag as 1, cool, it has shown me a p-value of 0.002, which is highly significant. So the value which will be observed on the next month is highly susceptible of the value or of the error which has been observed on this month. Any doubt so far? I'll be hopping towards AR.S, like seasonal auto regression model. But so far, any doubt? Like anyone thinking about why AR is not significantly implying but MA is? Anything like that? If not, then we should proceed. Now, it will, what AR.S.L12 does. So basically, it AR.S is checking the effect of seasonal component of lag 1. That means, is our output observed value of this month is affected by the observed value on the same month in last year. Okay, and we can see that it is not. So our observed value of next month is neither dependent on the value of this month nor the value observed on the same month last year, but it tells a different story in the case of moving average. So it says that there's a significant effect of the error predicting next month's value of the last year, same month of the last year. Okay, so we are having a p-value around 0.1018. Cool. How much this model is actually like able to explain things? So yes, there's a variance. So the variance denotes the difference in uh, month to month or season to season variation, which is 0 because it's a non-stationary data. We have converted it already, right? Now, with the help of this model, can we predict? Let's try that. So first I'll try to predict last 100 values or last 100 months. Okay, and I'll try to plot it along with the original data set what we have. And we can see there's a pretty overlapping diagram with we have a pretty overlapping diagram with a little bit of difference in here and there, right? So our prediction is not exactly accurate, but we can make sure with help of Sarima we are able to predict, right? Yes. So can anyone tell me how can we check how good the model is as a predictor? Anyone? Can you try? Like, we have a model. Generally, for any model we create, there should be two measures. How good it is explaining my pre-existing data, that is called model adequacy measure, and how good it can predict on unforeseen data, that is called the mm, I would say how goodness of predictor. Yes. So can you tell me any measure which I can come up with to measure how good a predictor this is?
By calculating the bias.
Executing the bias. You can think about it by estimating the error. Someone just suggested MSE. Yes, MSE is a thing, but this is that is something very squared, right? So we'll go forward with RMSE. What is RMSE? Root mean squared error. Root mean squared error. So in MSE, what we do? We square the error terms and take a mean. Here, we will square the errors at the first place and take a mean, then take the root value of that mean. Yeah, RMSE is also a loss function. MSE is also a loss function, and we are always trying to optimize that one only. So we are always trying to optimize the loss or the error so that we can get a better predictor, right? So loss function optimization is there always. Okay. Now what I'll try to estimate the RMSE from here. Okay. So from sklearn, I'll import mean square error, and then I'll store the forecasted values and actual values. And then I'll calculate the RMSE based on that. Cool. Now here we got a RMSE of 14.11. Okay. So in order to reduce the RMSE, what should we do? So far we have created a model, right? So far we have come up with a model. We have shown how good a predictor we have created or we have observed. But what if a model we got is not something we are satisfied with? So optimize the parameters. Okay, so Keshav, yeah. So which parameters you are talking about? Which parameters we should optimize?
So I have a question
Yeah.
just for the previous code. How do you predict the trend? What is the predicted data?
Like I have the model, right? If I am
Yes.
if I have the coefficients over here. So if I just put the value and
No.
multiply it and add them, if I am using an additive model, or multiply them if I'm using a multiplicative model, I'll get the YT, right?
So it is from Sarima model.
Yes, from Sarima model only.
Okay.
The whole prediction has been done with help of the Sarima model we have created with these particular parameters,
Mm. Yes.
where we have order 111 and seasonal order is 11112.
Mhm.
Okay.
Okay.
So suppose we are not satisfied with the RMSE. What should we do? One thing I did over here only, I assumed that the lag of AR should be 1. How come? Like I didn't do anything to estimate this one, right? I just arbitrarily told that I'm checking if this month's prediction, this month's observed value is dependent on last month's observed value or last month's error, right? It could be the case where it is dependent on uh, the predicted value of last of maybe 3 months before or maybe 6 months before, or could be dependent on that month's error as well, right? So this P and Q has been assigned to one as one arbitrarily. Now we should be coming up with a method by which I'll be estimating that. Okay. For that, I'll just try to find out the ACF plots and PACF plots. Wait a minute. Log differentiation seasonal, okay. Yes. Now we have plotted autocorrelation and partial autocorrelation plot over here. What can we observe from this? Can anyone tell me? What do you see in autocorrelation and partial autocorrelation diagram? Anyone? Just give it a try.
So area is constant in the second part.
The partial autocorrelation is more stable than the actual one, right?
Yeah.
Basically, it is told that if the spikes of the autocorrelation drops drastically after a certain lag, then that should be our value of P. Okay. So, sorry, that should be our value of Q. And if it is drastically dropped in partial autocorrelation, that should be dropped, considered as the value of P. So in partial autocorrelation plot, I can see after lag 2, there's a drastical drop, right? So I can assume that after 2 months, the observed value will be dependent on this month's error. Cool? And we will also estimate that after after lag 4, we can see a drastical drop in autocorrelation function. So our Q should be 4. Okay. So we should fit it into Sedima model, which will have a tuned parameter. Let me just paste it again. Tuned parameter as 4, 1, 2. Cool.
How can you get 4 and 2? Can you tell like 1 second?
Yeah. So basically, the what is the structure of the function? We have the order as P, D, Q, right? What is P? P is the parameter used in AR, like lag in AR. D is the number of differencing we did, and Q is the lag in moving average, right?
Yes.
Okay. So from partial autocorrelation diagram, if we see a drastical drop in the spikes after a certain lag, that means that should be our number of P. Okay. So we can see a drastical drop after 2, though there was a drastical drop after 1. So that would have explained better, hopefully, but we'll check for something else. This is the second best option for us. So we can see there's a drastical drop after 2. So P should be true, 2. Okay. Similar for Q as per the autocorrelation plot. Cool? Understood?
Auto correlation, it is 4.
Yeah, we can see there's a drastical drop after 4 here, right?
Okay.
Now we got a different model with help of study. Here we have lag 1, lag 2 and everything. For AR, everything for MA and seasonal lags as well for AR and MA. Cool? Now let's not dig towards the significance of the parameters or and all. Let us just think about how good this predictor is, how good this model is as a predictor. Let us plot it again. It shows almost same, but of course different. Let's find the RMSE of that model. Cool. Okay, so it is 13.48. So it's a better model. In spite of having a less drop in the spikes, it's a better model as a predictor. Cool. And there are different methods of estimating P and Qs as well. We can try that and fine tune our model for getting a better RMSE, or maybe we can work on some such data where we can test on unforeseen data set. Cool enough? Any doubts so far? Any doubt? Anyone?
So if the dataset has no seasonality, which model we can use?
We should go forward. No, if there's no seasonality, then there's no need of using Sadima. And in that scenario, Sadima and Edema work same.
Okay.
Should go for Edema. And if you are even if you are using Sadima and Edema is same basically. The
Oh,
effect of seasonality is 0. The
yes.
coefficient of seasonality is 0. So they
Right.
are same actually. There are scenarios where you can't get a good prediction with help of Sadima as well. Even there are some random errors, or the white noise is like complicated. White noise is dependent on something else. There's multicollinearity in the dataset. Then for that purpose, we can use ARG or GURG maybe. There are different models, but
Okay.
let's restrict that conversation. Yeah, Arijit, you said fair. Regarding what? Anyone have any questions apart from this? Then I think we can conclude over here. Any feedback, guys, from your side? I hope you enjoyed. Um, any feedback I would like to hear, like really appreciate the session. Enjoyed. Thank you. I'm hoping to see you guys again on our next session. Thank you. Also, I would be requesting to join our Google Space so that we can like discuss about it laterly. It shouldn't be restricted to a weekly event or a monthly event. We can talk about these different models and all. Also, we'll be giving you okay, how to join the Google Space. Yeah, I'll be sharing the link. Wait, shared it already. Though, wait a minute. Let me share it again. Yeah. So I'll be sharing the YouTube link, the PPT, which we shared, the collab, and the dataset all together. Also, guys, we'll be sharing a new dataset as well along with the other things. So I would recommend if you guys try these things on your own uh, for the practice purpose. Okay, so I guess you enjoyed. I enjoyed too. Uh, let's conclude over here. Thank you, guys. Thank you again. Have a good night.
Thank you so much. Good night.